Thank you. Hi, everyone. My name is Meryeme Boumahdi. I'm a PhD student at Politécnica de Madrid. And today I'm going to present one of our works entitled The Estimation of Daily Surface Reflectance Time Series Using Random Forest Model. In order to elaborate this presentation, I'm going to follow this order. So the context and this work is elaborated with the framework of FIRE-CCI project. It's a project with ESA, and the main objective of this work is to generate an annual global coverage time series table reflectance value using different sensors. And why we want this time series is that there will be an input for a burned area product. So MODIS is one of the widest used sensors, and it has many applications because of the good trade-off between the spatial, temporal, and spectral resolution. But it's one of the optical sensors, and they are suffering from one global problem, that is, they are dependent on the meteorological conditions. So that means even if we have a daily image, doesn't mean that we can use actually this image. And not all the pixels have a valid value. So we studied first the Terra and the Aqua sensors, and we had a conclusion that we cannot use only the sensors to completely fulfill all the pictures provided by Terra. So we decided to use Sentinel-2, Sentinel-3, that is one of the optical sensors that they have a closer characteristics of MODIS. So we studied the relationship and the overlapping between the bands in different sensors. And if you see here, the band near is overlapping. The three bands of the three sensors are overlapping here, the MODIS and all-key synergy and synergy SLSTR. But for the sphere, we only have two bands that are SLSTR and MODIS. So the main goal of the project is to provide a time series product with the characteristic of Sentinel-3. So it was important that we do some pre-processing for the MODIS, so they match the specification or the final specification for Sentinel-3. This the spatial resolution of 300 meters. And in the right, you can find the overflow of the pre-processing of the two tiles of Terra and Aqua to match it geographically to Sentinel-3. And actually, why we use two tiles? Because if you see here in the figure, one tile is not perfectly overlapping with the other tile of Sentinel-3. So we needed two tiles of MODIS to match to cover geographically the same area as Sentinel-3. Here I'm showing the study area, and actually we pre-processed two tiles. The first one is located in North Australia, that is known by forest fire every year. And the second one is located in South of America, that is including Colombia, Panama, and Ecuador. And here we use the data range from June 2019 to June 2020. And we should mention here that for the tile, the Australian tile, the reference, the sensor reference was Terra, and for the other tile, the reference was all-key. Why this difference? Because we want to make sure that we are using as much possible original value as we can. So we did a data analysis and we calculated the monthly average of percentage of valid value for every sensor. And here, the first tile that's corresponding to Australia tile, we have a good percentage of the valid values for Terra, while in the second one, we don't have really that much percentage. And by other sensor here, we mean Sentinel-3. So from here came that decision. So our approach consists of two steps. The first step is a spatial gaps filling based on machine learning, and we use the random forest model. The second step is a temporal integration and normalization by BRDF approach. Here is a summary of the whole pipeline of the work. In the left is the data processing that we applied to MODIS, and the second one is the random forest model generated. We use different attributes for the model, like the digital elevation, the orientation, the slope, the solar angles, the sensor angles, and the class, the land cover of each tile. Then we trained different models based on the sensor, so Terra Aqua, Terra Olki, Terra SLSTR, and then we picked the model with less error to estimate the pixels that we don't have, or the contaminated pixels with cloud or with the noise. Here, the table, I'm showing some of the errors of 7 different days with the number of valid pixels, and the last column is corresponding to the approach, to the global error of the approach. And the errors here and the order of the errors here is matching with the same order that you can find in different approaches in the literature. So in order to test the effectiveness of our approach, we calculated the normalized burn ratio for 2 different days for the 2 different tiles before and after the gaps filling. The column in the top is the image before the gap filling, and the one in the bottom is after the gap filling. We should note that this index only can be calculated if we have both values of near and SWIR. That means that if we are taking the 2 bands separately, it means that we have more values that we feel, that we estimate. Despite of this, we can see that we are increasing remarkably the number of pixels. But this project is conducted with burned area with fire, so it's not only important to study the effectiveness of the algorithm on the spatial aspects, but also we need to study the temporal behavior of the time series. So to do that and to validate the results, we choose 2 fire information. The first one is active hotspot catalog, and the second one is a fire mask provided by the firefighters. And here in the legend, each month is each color corresponding to each month. So it means that we have the location of the fire, but in an interval of a month. So the figures here show the time series of both near and the SWIR band for a duration of 1 year, from June 2019 to June 2020. For one point where the fire was occurred in September. And for the legend, we are using the sensors. So when Terra is the sensor, it means that Terra here at this point, at that day, are providing a valid value. Otherwise, the sensor indicated in the legend corresponding to the value of the surface reflectance that we use to estimate the value from. We also used Sentinel-2 composition images, and the composition is SWIR near read to highlight the fire, and the image is taken from the same day and from the same location to make sure that the fire was there. And we can see in the time series that the time series was having a stability over the time, but then we have a sudden decrease that is coincided with the hotspot and with the fire that we had from the fire mask. Here is another time series from the other tile, the South America tile. And we also have the same stability during the year, but there are some changes corresponding to the behavior of the vegetation. But also we have a sudden decrease of the surface reflectance for both near and SWIR that is coincident with the hotspot, but also with an image from Sentinel-2 that highlights the fire in that day. So as a conclusion, we can say that the proposed methodology allowed to generate a stable daily time series of surface reflectance for band near and SWIR. The estimated surface reflectance time series preserve a possible change due to the forest fire as an example, and we have a resolution of 300 meters. And it has been proven that it's possible to use multi-sources data for the target day that from that day that we want to fill without requiring any data from other dates that maybe we don't have. And then the methodology was able to remarkably increase the number of pixels in the image. And that's it, thank you.